Hello and welcome to the second part of our three-part webinar series on what's new in SigmaXL version 10. I'm your host, Paul Petrin, and today I'm joined by John Noguera, the co-founder and CTO of SigmaXL. John will demonstrate the new statistical tool, General Linear Model, and answer your questions at the end of the webinar. Participants will be muted, but please feel free to type in your questions. Note that support-related questions and questions not related to the content of this webinar should be sent to support@sigmaxl.com. So, without further ado, let me hand it over to John. John, the floor is yours.
Thank you, Paul, and welcome all to our webinar today. Happy to have you here. As Paul mentioned, we're going to cover general linear model with nesting, and we'll talk about the new features in GLM. Before I do start, just to mention that if you want to connect with me on LinkedIn, this is my LinkedIn address, so feel free to send me an invite. Our agenda for today, we'll introduce the general linear model. We'll talk about fixed and random factors, covariates, nesting, coding for categorical factors, main effects and interaction plots, pairwise comparison of means for fixed factors, and we will look at three examples: fixed factors with nested variable, sources of variation study, and an unbalanced nested factorial experiment with fixed and random factors. And then we'll do Q&A. All right, so to start, the general linear model, actually, let me just show you where it is in the SigmaXL menu. So under Statistical Tools, this is the new general linear model. Okay, so fit general linear model. And then when you click the fit general linear model, this is the dialog. And so I'll populate this in a moment with the first example, but I just want to go through some introduction. I want to talk about basically the different options here: fixed factors, random factors, covariates, and nesting. General linear model extends the advanced multiple regression so that you have support for fixed and random factors. We'll talk about what the difference is in a minute. Nested factors, covariates, and if you do have a random factor, or mixed random and fixed, and the design is balanced, you will get a variance components report. And the way it is calculated is using what's called classical expected mean squares. Now, something that we do in addition is we compute confidence intervals using a more advanced method called restricted maximum likelihood. Now, I'm not going to get into the mathematical details. These are available in the workbook appendix. We'll just focus on the interpretation of the software output. But this is just by way of background. So it's taking the advanced multiple regression and just adding a bunch of new features to it. And the focus is on the variance components report. If you have random factors, we're interested in the variance components report because that allows you to break out the sources of variation or do advanced measurement system analysis studies. Now, if the design is unbalanced, then the calculations are done using restricted maximum likelihood. And we have a fixed effects test using Satterthwaite approximation degrees of freedom. That's actually what we'll be doing when we do example 3. I've made it an unbalanced design. Now, I do recommend, if you are doing a variance component study, whether sources of variation or measurement systems analysis, that you make it a balanced design. It just makes everything easier. But if you do have unbalanced data, say, for example, one fixture has fewer operators than another, then it will be unbalanced and the calculations are more complex but more statistically correct. We also include main effects with confidence intervals and interaction plots. So main effects with confidence intervals, interaction plots, fitted means for non-nested fixed factors. That's an important thing, is that we are treating the factors as fixed when we are looking at main effects plots. Also, if we are doing pairwise comparison of means, we are interested in only fixed factors. All right. And we include the predicted response calculator, which is kind of nice. If you are doing sources of variation, you're typically not interested in running a predicted response or optimization. But when you do have all fixed factors, this becomes very useful because sometimes you have the nesting and you still would like to be able to do a response optimization or to compute a predicted response. In terms of recommended reading, if you have this textbook, it's chapter 13 and chapter 14 that I recommend as helpful for additional reading. So experiments with random factors, nested and split plot designs. We will not be getting into the split plot design portion, but the random factors and the nesting this is a good resource. So fixed versus random. A fixed factor includes data for all levels of interest. So suppose you only have 2 test machines in a plant. You want to include both in the study. That is a fixed factor. Whenever you do a 1- or 2-way ANOVA or multiple regression with categorical predictors, the factors are assumed to be fixed. Most people are familiar with fixed factors. Random factors have levels that are randomly sampled from a larger number of possible levels, but interest is in all possible levels. So, for example, in a gauge R&R study, you have part and operator. Well, part and operator are random factors. That is, you are taking a random sample of operators and you're taking a random sample of parts. Okay? If you only have 3 operators in the plant, then that would be a fixed factor. That wouldn't be a random factor. But typically you have many operators and you're taking a random sample of 3 from all possible operators, or you're taking a random sample of parts from all possible parts. But you're interested in the variability that speaks to the entire population. If a random factor is selected, you get a report called a VARComp on the sheet. It's called GLM VARComp. And this is the report that comes up by default. And so you can look at the variance components report. You can look at an analysis of variance and get your p-values. So that's quite useful. However, advanced options and confidence intervals for main effects plots are grayed out. All right, so when you select random factor, the choices become limited. You are not allowed to do stepwise regression, for example. In the GLM regression report, random factors are treated as fixed. Okay, so that's why the focus is on the VARComp report, not the model. But if you want to do some predictions, the way we do it is we treat the random factors as fixed. Now, there is something called mixed model, which is a more advanced version of modeling that takes into account the random factors and does things like what are called best linear unbiased prediction, marginal fitted equation, conditional fitted equation. So we don't do any of this. Okay, so I just want to be clear that this is an extension of GLM, but is not full mixed model. All right, and the focus is on what is typical for Six Sigma practitioners: sources of variation studies and measurement systems analysis, non-traditional or advanced measurement systems analysis. A couple of technical points. If there are more than 50 unique levels, a warning message is given, okay, because that's typically, you've mistakenly selected a continuous variable as categorical, so you get a warning message. It's best to avoid asterisks or parentheses in the names, because the asterisk denotes multiplier and this denotes nesting. So the parentheses denote nesting. Avoid the use of those in your column headings. Covariates are simply continuous numeric variables of interest. And the same rules apply to covariates. Also, of course, if it's a covariate, text is not allowed. It has to be numeric. So nesting. When you check the nesting, and just by the way, let me flip over here. That's this checkbox right here. Of course, you can't do that because we haven't selected anything yet. But this checkbox is the nesting. So you check nesting to include nested terms in the model. The left side drop-down selection can be a factor or a covariate, and the right side drop-down is a factor. This will create a term with the notation A parentheses B, where A is nested in B. So in the example that we'll actually be using, we're going to use the customer data, and we have product type nested within customer type. So product type is consumer manufacturer, but it's consumer underscore one is the consumer underscore customer type one. And then manufacturer underscore one is the manufacturer nested within customer type one. Then you have consumer two, which is consumer nested within customer type two, and manufacturer nested within customer type two, consumer nested within three, and manufacturer nested within three. All right, so that's the example that we'll be using. Another example is if you have three locations and you have operators at each location. Obviously, these are different people. So operator is nested within location. So you would use the notation operator parentheses location. A maximum of 3 levels of nesting are permitted with up to 4 factors. You have to be careful. You can't say A parentheses B, B parentheses A, because that means it's nested within itself. That's illegal. And you'll get an error message. Also, indirect nesting within itself. A nested in B, B nested in C, C nested in A is also illegal. All right. Now, if B is nested in A, or A is nested in B, the interaction term of A times B is not permitted. All right, because once it's nested, you can't compute an interaction term. Now, when you select interactions, SigmaXL will automatically exclude these in the dialog. So you don't need to worry about that because they just won't be available as an option. However, interactions involving A or B with other factors are permitted. And in fact, we will do that in the third example. Term hierarchy is recommended but not required. And if you want further information, see the SigmaXL workbook appendix, nested factors and coding and nested covariates. Coding for categorical factors, this is actually identical to what is in advanced multiple regression. The only difference is the coding for categorical factors -1, 0, +1 is the default. In the advanced multiple regression, the dummy coding 1, 0 is the default. Okay, so we've changed the default. And the reason for that is that because this particular coding scheme results in lower multicollinearity than the dummy coding. And the reference level is the last alphanumerically sorted level and is hidden in the parameter estimates table. All right, so that's coding. Main effects and interaction plots. We've added confidence intervals to the main effects plots. Those are not in the advanced regression. Note, we use fitted means, not data means. If an interaction term is not in the model, the interaction plot is still displayed, but it is shaded gray. If a random factor is selected, confidence intervals for main effects plots are grayed out, as we mentioned earlier. Also available, if you have fixed factors, pairwise comparison of means. Pairwise comparison of means examines the difference between all combinations of the estimated means for each category of a factor, along with the standard error and the confidence band for the difference. The default is Tukey, which provides protection against false positives due to multiple comparisons. Fisher is also available. That does not take into account the problem of multiple comparisons. All right, so that's pairwise. If the model is not hierarchical, the pairwise comparison report is not available. And here, for further information, see the workbook appendix. And we are ready to start our example. So we're going to use the customer data. The first thing I want to point out for this example, the data is not actually nested, but the customer data is something that we use throughout the workbook with overall satisfaction, customer type, product type, responsive to calls, ease of communications, overall sat on a 1 to 5 score, where 5 is very satisfied, 1 is very dissatisfied. And we have responsive to calls on a 1 to 5, ease of communications on a 1 to 5. So this data we have analyzed throughout, and I wanted to start with data that was familiar. So what we're going to do here is we're going to say product type is nested within customer type, just so that we can actually demo how everything looks and how everything works. You do want to standardize your covariates. So because we're using covariates here, which are responsive and ease, you will want to standardize those as you do when you're doing multiple regression. All right, so let me switch over to SigmaXL. I already have this set up from before, so I'm in customer data, and I want overall satisfaction as my Y. I want my fixed factors to be customer type and product type. Now, once I've selected fixed factors, I'll select my covariates as well, which are responsive to calls and ease of communications. These are continuous predictors. I check my nesting, and on the left side, you can select a factor or a covariate. We are going to select product type nested within customer type, as we illustrated earlier in the diagram. So just one level of nesting. By the way, you are allowed 3 levels, okay, which is quite a bit, but that's the limit in terms of SigmaXL. So basically 3 levels of nesting with 4 factors. Advanced options are available because we didn't specify random factors. So this is where your pairwise comparison of means for fixed effects comes in. We're not going to run stepwise. We're just going to use all the defaults. We're not going to change anything here, but just to point out that because we didn't specify a random factor, the advanced options are still available, and we want to standardize the covariates. So now when I click Next, I'm prompted with the Specify Model Terms dialog, and I'm just going to select all. Actually, no, sorry, I want interactions. I want to add two-way interactions. So when I add the two-way interactions, one of the things you'll notice is that you have responsive to calls by ease of communications and so on, but you do not see product type by customer type. That is because that's an illegal interaction, because product type is nested within customer type. So it's not even available as a possible item to select. We're only going to pick the first 5 terms. Based on previous analysis, we know responsive by ease is an interesting interaction. So we're including that. So we have responsive, we have ease, we have responsive by ease, and then we have customer type, and then product type nested within customer type. All right, so now we run the report. And this is our model report. Now remember, we did not specify a random factor. So because we did not specify a random factor, we do not get a source of variation report. We only get the regression model. Just a couple of things to point out: that you'll notice that customer type 3 does not appear. That's the hidden reference value. Basically, it's a linear combination, so it's not needed. It's used in the formula for making predictions, but in the actual parameter estimates, it doesn't show up. So it's a hidden reference level. Similarly, manufacturer doesn't show up because it's the hidden reference level. So you have product type nested within customer type, consumer, customer type 1. Product type nested within customer type, consumer for customer type 2. Product type nested within customer type, consumer for product type 3. These are the different coefficients. So depending on what you plug into your predicted response calculator, this is used to make the prediction. Okay, we can look at the p-values. The easiest way to do that is to look at the ANOVA for predictors, and we can see that responsive to calls are significant, ease of communications are significant, customer type is not significant, but we will leave it in the model because product type nested within customer type is significant. And then, of course, the interaction of responsive by ease is significant. So just really wanting to point out the difference between, say, a regular regression report and the regression report with nested terms. All right. Now, let's say we want to maximize customer satisfaction. I'll come over here, I'll do maximize, and I'll run optimize. And then click yes. And this gives me the combination, no surprise, responsive to calls 5, ease of communications 5, and then customer type and product type that maximize the predicted response. You can see here from the Pareto that customer type is not significant, but product type nested within customer type is significant, just significant. All right. The next thing I want to look at is the pairwise comparison of means report. And this does not show the nested term, it only shows the top level. The number of combinations becomes it just becomes too messy when you get into the nested, so we only include the top level or the non-nested fixed factors. So difference of means shown here, the difference of levels, the difference of means, the standard error, and the p-values. All right, so nothing is significant here. This is for customer type, so no surprise, we saw that in the regression report, customer type was not significant. So in the pairwise, we're not seeing anything significant here as well. Now, one thing I did forget to do, so let me just do a recall SigmaXL dialog, is I wanted to turn on the main effects plots with the confidence intervals and run that. So I just rerun. So now we'll get the main effects plots. So here we see responsive to calls has the steepest slope, followed by ease of communications and customer type. Customer type, as you can see, there's lots of overlap on the confidence intervals, so it's really not a significant factor. All right, so that's the main effects plot. And that's really all I wanted to do for example 1 was, as I said, no surprise, this is something we've looked at before. Responsive and ease are the primary factors that drive overall satisfaction. But I wanted to include the aspect of nesting and just show you how that plays out in the report. Now, typically with nesting, you will have random factors, and that's what we're going to get into with example 2, which, let me come back to the PowerPoint. And we're going to look at multivariate data. So we're interested now in sources of variation. And what we have in this multivariate data, I drew a diagram to illustrate what the structure of the data is. So you have time 1, time 2, time 3. This could be day 1, day 2, day 3, week 1, week 2, week 3. And then within each time, we have unit 1, unit 2, unit 3. However, this unit 1 is different from this unit 1. This is unit 1 nested within 1. This is unit 1 nested within 2. Unit 1 nested within 3. And then at the bottom, we have replications. So within each unit, we have 9 measurements. So what we're interested in is what's the dominant source of variation? Is it temporal, time to time? Is it between unit? So unit to unit, or is it within unit? Is it the source of variation at the lowest level is also known as the error term? All right, so we're interested in within unit, between unit, and temporal, and we want to analyze each one of these. Now, one of the ways you can do this is with a multivariate chart. So to save time, I'm not going to actually produce the charts, but I will show you the PowerPoint. They've already been done. And you just simply go to SigmaXL Graphical Tools, Multivariate Charts. So the within data looks like this, and you can see the long bars showing you that the within is the dominant source of variation. You're not seeing much unit to unit variation, nor are you seeing much week to week or time to time. All right, this is the overall mean for time 1, overall mean for time 2, overall mean for time 3. So the dominant source of variation here is within. This is dominant is between. So you can see your unit to unit showing lots of variation. That's your dominant between unit source of variation. And this is your dominant temporal. So you can see time 1 versus time 2 versus time 3. Okay, you have that as your dominant source of variation. Now, what this is useful for is in process improvement, variation reduction. If you understand what your dominant source of variation is, then that's going to allow you to focus on the area that you get the biggest bang for your buck, your improvement effort. So depending on which one of these comes up as a dominant source of variation, it's helpful for you to apply the appropriate process improvement methodologies, doing your experiments in the right place, your control charts, and so forth. And what this will do now, what we're going to do with the GLM is we're going to quantify what we see here graphically. We're now going to quantify the sources of variation as percentages. So we'll be able to take those percent contributions, variance components report, and come up with a quantitative number. So with that, I'm going to switch back to general linear model. And I'm going to go to the multivariate data. And I'm going to start with the within. So I have my measurement, I have my unit, I have my time. One of the things we don't have is a column that shows replication. One of the things you do not want to do whenever you're doing a source of variation assessment, you do not want to include the lowest level. You need the replications in order to be able to estimate the error at the lowest level. If you include that in the model, then it's going to treat that as a factor and won't be able to estimate the variance components. So that's something to keep in mind. The lowest level is never included in the model when you're doing source of variation studies. So SigmaXL, Statistical Tools, General Linear Model, and I'm going to do a measurement as my Y. Now I'm going to just switch the order here. I'm going to put time on the top, followed by unit. And then the nesting is unit nested within time. Okay, we saw that in the diagram. I'm not going to turn on main effects plots. Notice advanced options are grayed out. As I mentioned earlier, once you select random factors, you can't do stepwise regression, for example. You can still do box-Cox, but you can't do stepwise. Nor will you get a pairwise comparison report. You will get a regression report, but that assumes that the factors are fixed. So it's just kind of a supplementary information. The main thing that we want here is the variance components. I'll select all, click OK. And this is my variance component report. I can see here the response is measurement, factor coding, design type, it's balanced, it's hierarchical. The methodology used, expected mean squares with restricted maximum likelihood confidence intervals, factor information. Here's my GLM ANOVA. This shows that time is not significant, that unit is not significant. And if you look at the variance components report, you can see error contributes to 100% of the total variation. All right, so the within, or the error term, is the dominant contributor. In fact, you have negative variance components. When you have negative variance components, these are just treated as 0. And confidence intervals are not given for negative variance components. So basically, here we have a confidence interval for the error variance component. Also for convenience, but we're not going to use that here, are the square root of the variance components, showing you the standard deviations and the percentages of standard deviation. That becomes more useful when you're doing MSA or gauge R&R. And in the third webinar, we're going to do gauge R&R using GLM, and we'll be using this portion of the report. For now, we're just interested in the contribution to the variance components. All right, so this is the regression report. Remember, this treats the random factors as fixed, okay? Now, typically, when you're doing an SOV study, source of variation study, you're not interested in doing predictions of random factors. But if you are interested, what would it look like if these were fixed factors? Then at least you have some ability to model that. All right, so it's more of just a convenience item. The primary focus, once you have that random factor, is this variance components report and the GLM ANOVA. All right, let me go to the PowerPoint slide. And this is the between. And in the between, you can see the unit nested within time is 98.3%. So that's the dominant source of variation. And the error term is 1.74. And you can see here that unit is significant. So again, this helps you to say, where are you going to focus your improvement effort? Well, in this particular case, it's the unit-to-unit variation that needs to be focused on, and the root causes associated with that particular source of variation. Finally, the temporal, you can see here the variance component is 98.5% for time, and the others are very small. All right, so you have these three examples showing you clearly which bucket is the biggest. Oh, also here you can see that both factors are significant. So this SOV study allows you to identify the variance components, what is contributing to the variability, and giving you then a good direction for further improvement, for further process improvement, further variation reduction. All right, so that's a very useful tool and should be used in complement with the multivariate charts as we introduced this example. So finally, example 3. Now we get more tricky. We have both fixed and random factors. And the example comes from the Montgomery textbook, and it was modified to turn it into an unbalanced design. Okay, so it's called assembly time nested. And the process is the hand insertion of electronic components on a printed circuit board. The goal of the study is to improve the speed of the assembly operation. The design includes 3 assembly fixtures and 2 workplace layouts. Operators are required to perform the assembly. In the book, 4 operators are randomly selected for each fixture layout combination. Here, however, we will use 4 operators for layout 1 and 3 for layout 2, making it an unbalanced design. The operators chosen for layout 1 are different individuals from those chosen for layout 2, so operators are nested within layout. Because there are only 3 fixtures and 2 layouts, these are fixed factors, but the operators are random factors. So it's a mixed model. The treatment combinations in this design are run in random order, but the worksheet is shown in standard order. 2 replicates are obtained, and the assembly times are measured in seconds. So with that, we'll switch over and run the general linear model for assembly time nested. By the way, these data sets are all available under help sample data. Okay, so customer data, the multivariate data, and this assembly time nested come with the SigmaXL installation. So there's no need for additional download. So here's the reference, and this is fixture, layout, operator, time. So we want to go to Statistical Tools, General Linear Model, Fit General Linear Model. And I'm going to select time as my numeric response, the Y. Remember, fixture was fixed, layout is fixed, and operator is random. We have nesting. Operator is nested within layout. We do not have covariates. And I will turn on the main effects plots and the interaction plots. Notice that the confidence intervals are unchecked and the advanced options are grayed out because we selected operator as a random factor. We're not going to use Box-Cox transformation here. Okay, so with that, we'll click Next. And we will specify two-way interactions, main effects plus two-way interactions. And you'll notice that operator by layout is not available as an option. That would be illegal. All legal options are presented, which includes operator nested within layout, fixture by layout, and fixture by operator nested within layout. So we select all, and then we click OK. And this gives us our report. Now, notice, the report is using restricted maximum likelihood because it's an unbalanced design. All right. So the difference here is you don't get the full ANOVA. What you get is the test of fixed effects. And the other difference is under the variance components, you get a z-test with the p-values. Now, unfortunately, this z-test is not as powerful as the f-test in the ANOVA. So it's far better to use balanced data, all right? If you have unbalanced data, mathematically, statistically, you really should be using restricted maximum likelihood to get the proper variance components. The trade-off, however, is that we don't really have, this is just not very powerful, okay, because the variance components can be quite wide. As you can see here, operator from 0.3 to 9.9, so it's a very wide because of the sample size. So it's not a powerful test, but the tests of fixed effects are quite useful. Like I said, if you have balanced data, the analysis is easier. If you have unbalanced data, you do get the proper report, but you lose the full ANOVA table. Here we see that operator contributes to 34% of the variation. Fixture by operator contributes to 14.8, and error, that is the within term, is 50.8. All right, so the within term is the dominant contributor. And remember, the goal is to reduce the assembly time. So at the lowest level, the replications, we're seeing that we have variability. So that's going to be kind of hard to really do anything with that in terms of saying, what do I need to do to help me to improve? But at the lowest level, you're talking about replications. There may be some, maybe there are some systematic process things that can be done to reduce the variability at the replication level. But the main thing that I want to bring out here is the fact that fixture is significant. And if you look at the plots, you can see right away fixture 2 has a large mean assembly time versus fixture type 1 and 3. So right there, that tells you that's where you focus your improvement efforts. That's where you need to put your efforts to say, is it something about fixture 2 that's more complicated, more steps that we need to address in order to reduce the assembly time? So looking at the main effects plots, the fact that it was statistically significant and looking at the main effects plots make it obvious where the improvement effort needs to be made. So that's my example 3. And I wanted to use this because it is a more complicated example because it includes both fixed and random. It includes nesting. And it's unbalanced. So that's, I wanted to kind of include that. Typically, however, if you can, keep it balanced, and that makes the analysis much simpler. So that actually concludes my presentation.
Thank you, John. We'll now open up the floor to the Q&A portion of the webinar. So, John, here's a question. Can you please show me where the examples are given in the SigmaXL workbook?
Okay, thank you. That's a great question. So if you are in SigmaXL and you go to Help and you go to SigmaXL Guide, that brings up the SigmaXL workbook. And then you can go to Table of Contents. And in the Table of Contents, under here we have the General Linear Model. So you can go to the General Linear Model section in the Analyze phase. And this gives you more information on your dialogues and options, basically the content I covered just in more detail. And then the examples are here. This is your first one, fixed factors with nested variable. And then sources of variation. By the way, example 3, we're going to do in the third webinar. We're going to look at gauge R&R studies using GLM. So that will be example 3. And example 4, operator is a fixed factor. Example 5, gauge R&R study with operator in one part. Destructive gauge R&R. Expanded gauge R&R. So we'll be looking at all those in the third webinar. And this is example 8, unbalanced nested factorial with fixed and random factors. Also, just to mention, in the appendix, there's more technical information. You have more information on how nested factors are computed, how the coding is done, what happens if there are covariates, how restricted maximum likelihood is computed, and pairwise comparison formulas and references. Okay.
Thank you, John. Here's another question. Are nesting errors flagged or just excluded?
It depends on the error. So let's go back to multivary. Let's actually do it incorrectly. So we're going to do, so what I'm going to do is I'm going to go unit nested in time, time nested in unit. And then we'll go, so general linear model. So measurement, unit, time. And I'm going to go unit nested in time. And then we're going to go time nested in unit. Now, watch what happens. When you click next, there's an error in the nesting specification. Okay, so basically it stops you from making an incorrect setup. That assessment will be direct or indirect. And then, as I mentioned on the combinations, then the way that's handled is simply by not even presenting an illegal combination as an option. Okay.
Thank you, John. So this concludes the second webinar in our three-part webinar series on the new features in SigmaXL version 10. I hope you found this session useful and informative. PowerPoint and the example datasets used in today's webinar will be available for download on our website, and a recording of the webinar will also be available for download within the coming weeks. In the next and final webinar in this series on Thursday, September 28th at 3 p.m. EDT, we'll explore the new MSA templates, as John said, and statistical tools in version 10. Thanks all for joining us. We look forward to seeing you during the next webinar. Have a great day.
Thank you. Thank you very much.